Alright, as we move into chromatography, Chapter 23 deals with some basic chromatography information and how we talk about chromatographic processes. And then as we get into further chapters, we'll deal with specifically gas chromatography and liquid chromatography this semester. You may be familiar with separations mostly from organic, where you did separations in your separatory funnel. While we don't often think about it as being an analytical technique, it can be if we know some of those parameters to a high degree of certainty. So let's take a look real quick. This is Chapter 23, Analytical Separations. So we've got two phases. Let's say we have an aqueous and a organic phase. This is in a beaker, but it works similarly in a separatory funnel. Right? In a separatory funnel, you can shake it so that those layers mix better. The more you mix those two layers, the more the surface area, because you make these bubbles and emulsions that you might have talked about in organic. The more of that surface area, the better the transfer is going to be from one phase to the other. Right? But we set up this equilibrium, and we can talk about this equilibrium, K, between these two. And if we start in 1 and we go to 2, then our product is 2. So the concentration of our sample in phase 2 divided by the concentration of our sample in phase 1. Instead of calling this an equilibrium coefficient, we call this the partition coefficient. And so this partition coefficient K is larger, obviously, if our solute, our sample, prefers the second solvent, and it's smaller if our solute or our sample prefers the first solvent. Okay. If we're doing this analytically, we want to know how much of our sample is actually being extracted. And so if we have a K of, I don't know, let's say 3, right? Then that means that there are 3 times as much of our sample in the second solvent as there is in the first solvent. And that's a pretty efficient extraction if I can get 75% of my sample extracted each time. Okay. The textbook goes through this derivation more completely. So if you want to look at that, do look at that. But we're going to use Q as the fraction of our solute, S, that remains after extraction. Okay. And if it's remaining, obviously that's in solute 1. Okay. So from K, which again is the concentration of our solute in the second solvent divided by the concentration of the solute in the first solvent, this is equal to 1 minus Q. So that's the fraction that moves over, right? If Q remains, 1 minus Q has moved into the other solvent, times the number of moles that we have. Right? So this is the fraction times the number of moles divided by the volume of the second solvent. And then the concentration in the first solvent is just Q, that fraction that remains, times M, so the number of moles, times the fraction, divided by V1, the volume of that first solvent. And so we can rearrange this a little bit, and we end up with Q, that fraction remaining, is equal to V1 divided by V1 plus K V2. Now, if we do multiple extractions, I don't know if you did this in organic or not, but it's typical to do more than one extraction. And the reason we do that is because we square or cube the amount of material that we're able to get. Rather than just adding, we actually have this factor here, this exponential factor. Okay. So we're going to use these equations. Let's do a quick example. We have a partition coefficient of 3, so K equals 3, between toluene and water with 3 times as much in the toluene phase. So toluene then must be S2 and water must be S1. So we have 100 milliliters of a 0.1 molar aqueous solution that are extracted with toluene. And so let's see if we do it as 1 500 ml extraction versus 5 100 ml extractions. So remember, Q is equal to V1, that's 100 milliliters, divided by V1, again, 100 milliliters, plus K, which is 3, times 500 milliliters. Okay, so this is for our one extraction, and we end up with Q being about 0.06, so that's about 6%. Okay, so one 500 ml extraction, we get 94%. That's not terrible. But what if we do it with 5 100 ml extractions? Q is equal to 100 mils divided by 100 mils plus 3 times 100, all of that raised to the 5th. Right? When we do that, Q is equal to 0.00098, or about 0.1%. We've used the same volume of toluene, but we've done it in different fractions, so we get a higher percentage extracted. That coefficient, that partition coefficient, tells us what fraction will be extracted during each extraction. If we do more extractions, then we will end up extracting more than if we extract with just a larger volume. Okay? All right. So, moving into chromatography from separations. Chromatography is where we take some sample and we try to separate those components, so it is a separation, but we try to separate those components on what we call a column or a stationary phase. So you have a mobile phase that's moving all of the components along, and you have a stationary phase that those components might interact with or might not as they move through the column. And so here, in green, in the light green, we have our column packing. That's the stationary phase. Okay? And we have our solvent here, which is our mobile phase. Okay? And as the solvent pushes through, this is just a gravity chromatography. This is about as simple a chromatography experiment as you could do. As the solvent pushes through, the components that are in that initial band here begin to separate out. I don't know how easy it is to see, but we have a green and we have a blue. Let me color all of the B's here blue. And after a little bit of solvent, they've separated just a smidge. After more solvent, they separate even more. After a good bit of solvent, B already starts to come out, and then it takes a whole lot more solvent for A to come out. Sorry, my webcam there is blocking that, but that's as A emerges. Right? And so clearly, between these two, component A interacts with the stationary phase more than B. Right? Whatever compound B is does not interact very much with the stationary phase. He pulls right through. Right? He comes out real quick. whereas A takes a little bit longer to elute. Okay? Elute is the verb for coming off a column. We have this mobile phase, this solvent that we are using to push those samples through. It's called the eluent. And then the actual stuff that comes out, those droplets, are called the eluate. But the process is called elution. Okay? And so that's the basic principle for chromatography. What's actually happening is that you are partitioning. So just like we had that partition coefficient between solvent 1 and solvent 2 for our separatory funnel, here we have a partitioning not between two solvents, but between the mobile phase and the stationary phase. Right? That's our S1 and S2, right? So think about this as S1. Think about this as S2, even though we're going to talk about those as M for mobile phase and S for stationary phase. And so we have a couple different varieties of columns. We'll talk more about those when we talk specifically about gas chromatography and liquid chromatography. But generally speaking, you can either have lots of little particles, almost like sand. I mean, it's very fine powder that is stationary phase that our liquid has to flow through. Or you can have a very thin column, just not much wider than a hair, that's hollow in the middle, but the inside of that column is coated with a material, the stationary phase material. And so we'll talk about 5 broad categories of chromatography, and then we'll do some more discussion of the different types. And so adsorption chromatography, we have a solid SP here is stationary phase. And MP is mobile phase. And so in adsorption, we have a solid stationary phase, we have a liquid mobile phase, sometimes a gas, but often a liquid mobile phase. And whatever your solute is actually adsorbed onto the surface. So I don't remember if we talked about this in class or not, but we have adsorption and absorption with a B. To absorb something is to soak it up like a sponge, right? And so when you're cleaning your dishes off, all that dishwater gets soaked into the sponge. Adsorption is when you have a particle that sticks to the surface. So that leftover bit of lasagna sticks to the surface of the sponge, adsorbs, but it doesn't soak into the sponge, absorb. Okay, so only a D versus a B, but adsorb just means it sticks to the surface. And so you have that solute particle that sticks to the solid stationary phase. It doesn't absorb into it. And so it's not really a partition like we talk about in the separatory funnel example. Right? And so if we have this, the stronger the absorption, the longer it stays on the column. The longer the retention time. We'll get there in just a minute. The second variety of chromatography is partition chromatography. That's the one we talked about just a minute ago. And that's here. This is that hollow tube, hollow capillary type chromatography that I mentioned, where we have this small column. Again, these are not this big. They're about the diameter of, they're bigger than a hair, but not by much. And coated on the inside of that column is this thin layer of stationary phase. These stationary phases are often carbon chains, and so think about it almost like a sea anemone, right? You've got this stationary phase that is connected to the column, right? But it's still possible for the solute particle to no longer be in the mobile phase, but to be in the stationary phase. Ion exchange is a pretty straightforward one. When we have ion exchange, we have ions of interest that are in our sample, and we exchange those with ions that are already in the column. Right? And so we have something that's bound to that column. So if we have an SO3 minus, for example, maybe our counter ion will be sodium plus. If we have this trimethyl ammonium, maybe our counter ion will be something like Cl minus. And what happens is, as your sample passes through, maybe it turns out that strontium has a higher affinity for sulfite than sodium does. And so the strontium gets caught on that stationary phase, pop off of sodium, and that sodium can travel down with the mobile phase. Let's say that sulfate has a higher affinity for that trimethylamine than chloride does. So the sulfate comes in and binds, that chloride gets popped off and travels down the state in the mobile phase. Okay. The reason for doing this is because maybe we sometimes want to get rid of those ions completely and we don't want them in our sample. This is the case in a water softener. South Carolina has generally pretty soft water anyway, but if you've ever lived somewhere where the water was hard, you would have had to deal with a water softener where there's this resin that exchanges sodium and chlorine for things like magnesium and phosphate. The magnesium and phosphate get left behind in the water softener system, and the sodium and the chlorine get released, which are softer, give softer water than things like magnesium and calcium, stuff like that. The last two methods include molecular exclusion and affinity chromatography. In molecular exclusion or size exclusion chromatography, what we have is we have this network. Our stationary phase is like a gel, and it's got some pretty large paths that go through it, but also some small sort of windy paths that go through it. It turns out that the larger the particle is, the easier it goes through that larger path, and so it actually comes out first. The smaller the particle is, the more it gets lost in all the side paths on the side roads, and it takes longer for those smaller particles to come out. And so in molecular exclusion or size exclusion chromatography, we get the large particles come out first, and then as time goes on, we get our smaller particles that come out last. The last kind of chromatography we'll talk about is affinity chromatography. This often uses some biochemical pair, an antibody and an antigen, for example, or a protein and the thing that goes in the active site. You can tell I'm not a biochemist. But if you have their stationary phase that's, say, coated with antibodies, if that antigen is in your sample as it goes through in the mobile phase, then that antigen will latch onto that antibody and not go out the column. Those interactions are very, very specific, and so affinity chromatography is a great way to separate things if you have if the ligand that you're interested in has a corresponding antibody or receptacle, receiving molecule. All right, that's the first part of chromatography. We'll stop there. The second part of chapter 23 is coming shortly, and then we'll jump into gas chromatography. Take care.